Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss all the concept regarding parity operators. Let's begin. Parity operator. A parity operator changes the sign of the space coordinate at the Hilbert space coordinate of any function upon which it operates, and it is denoted by the symbol pi cap. That means it indicates when that parity operator pi cap operates over a function, let that function be f of x, it changes its sign, means f of x changes to f of minus x. This is the definition of parity operator. When that parity operator operates over a function, it changes its sign. Now, we have to show the Hermiticity of parity operator. For arbitrary functions, let we choose, let psi 1 and psi 2 be arbitrary wave functions. Then the integration over minus infinity to plus infinity psi 1 star pi cap psi 2, that is psi 1 is a function of x, psi 2 also is a function of x dx. What should be its value? When that parity operator operates over the wave function psi 2, it will be changed its sign. That means integration over minus infinity to plus infinity psi 1 star x psi 2 minus x dx. Let equation number 1. Now, changing the integration variable from x to minus x in that of RHS of that equation, means when we interchange the sign as x, we replace as minus x. What we have? Again we write here, changing the integration variable from plus x to minus x in the RHS of equation 1, we get that will be changed to what? Just I write, that is integration over minus infinity to plus infinity psi 1 star minus x psi 2 x d of minus x. Just we replace positive as negative, that is d of minus x minus to that of outside, integration over minus infinity to plus infinity psi 1 star minus x psi 2 x dx. Psi 1 star minus x, that can be replaced by integration over minus infinity to plus infinity that can be written as pi cap psi 1 x conjugate psi 2 x dx. When that operator operates over psi 1 x, that gives rise to psi 1 of minus x and psi 1 star of minus x. What it indicates, look here, that particular term, that particular integral can be written in that of form. That form is nothing, that is the representation of hermiticity of a particular function, or sorry, hermiticity of a particular operator. This equation shows that the parity operator is Hermitian. So therefore from this equation we conclude that pi cap, that is parity operator is Hermitian. We know the eigenvalues of a Hermitian operator are real. That's why the eigenvalues is must be real. So its eigenvalues, since it is Hermitian, its eigenvalues are must be real, are real. Its eigenvalues are real. Let us withdraw what should be the eigenvalues and eigenfunctions of the Hermitian operator. Let us derive the eigenvalues and eigenfunctions of that of Hermitian operator. Now the eigenvalues equation, the eigenvalues equation for parity operator, pi cap is when that parity operator operates over a function, let psi alpha of x, it gives rise to alpha psi alpha x, that is equation number 1, where psi alpha x is the eigenvalue of, where psi alpha x is the eigenvalue of pi cap belonging to the eigenvalue alpha, its eigenvalue is alpha. If that parity operator operates from the left on that of equation, what we have, if pi cap operates from left on both sides of this equation, we get, that is pi cap square psi alpha x will be alpha pi cap psi alpha of x, or that will be pi cap square psi alpha x is equal to alpha square psi alpha of x. That is equation number 2. But we know, but that can be further written like this, but pi cap square psi alpha x written as pi cap psi alpha of x. That means pi cap, when that parity operator operates, that is psi alpha of minus x. Again that parity operator operates, again sign will be changed, psi alpha of x. That is the value of what? That is the pi cap square psi alpha x. Pi square psi alpha x will be this much, that value will be that much. That equation number 3. Now comparing equation 2 and 3, what we have? Comparing equation 2 and 3, we get the value of alpha square will be 1, alpha square will be 1, which implies alpha value varies from plus minus 1. Equation number 4. Therefore, the eigenvalues of that parity operator are plus and minus unity. So, the eigenvalues of the parity operator are plus or minus unity. Now, denoting the corresponding eigenfunction, denoting the corresponding eigenfunction, let for that of plus we take as psi plus of x, and for that of minus let we prefer psi minus of x. That is when that parity operator operates over psi plus of x gives rise to plus 1 psi plus of x. Again, when that parity operator operates over psi minus of x, it will be gives rise to minus 1 psi minus of x, which implies, look that equation, when that parity operator operates over that, it gives rise to psi plus minus x. Just change the sign, that gives psi plus of x, that value will be even function. But when psi minus of minus x, that gives rise to minus 1 psi minus x, that is known as the odd function. This is very useful in case of that eigenvalues of eigenfunctions of that of parity operator. This is the eigenfunction equation. Now, the orthogonality of psi plus and psi minus, we have to prove the orthogonality of that of psi plus and psi minus. Since the parity operator pi cap is a Hermitian, then according to the definition of Hermiticity or the condition of Hermiticity, we write the integration from minus infinity to plus infinity psi plus star pi cap psi minus x dx, that is psi plus x, is equal to integration from minus infinity to plus infinity pi cap psi plus x star psi minus x dx. Or when that parity operator operates over that of wave function, it change its sign, means that is integration from minus infinity to plus infinity psi plus star x, and that value gives rise to minus psi minus x dx is equal to integration from minus infinity to plus infinity. Again we use the definition of that of parity operator, that is plus 1 psi plus x and its conjugate psi minus x dx. Okay, taking its conjugate as minus infinity to plus infinity psi plus x star psi minus x dx, and that value, that is minus to that of outside, integration over minus infinity to plus infinity psi plus star x psi minus x dx is equal to that one. When this to that side, there will be 2 times of that integral, or that is 2 integration over minus infinity to plus infinity psi plus star x psi minus x dx is equal to 0, or that is integration from minus infinity to plus infinity psi plus star x psi minus x dx is equal to 0. The integration of these two will be 0. We can say so psi plus and psi minus are orthogonal. Psi plus and psi minus are orthogonal. So we can take a question here using that of parity operator. What should be the Hamiltonian, what should be the operator value of that parity operator and the Hamiltonian operator? What should be the commutation relation between these two? Where pi cap is the parity operator. So to solve that type of problem, choose a arbitrary wave function, let f of x, if f of x is an arbitrary function of x, and we prefer the potential v of x be v of minus x. The potential is symmetric, means v of plus x is same as that of v of minus x. Therefore, that commutation relation pi cap h cap of x when acted upon that function f of x gives rise to pi cap h cap x f of x minus h cap x pi cap f of x is equal to parity operator operates, it gives rise to change its sign minus x f of minus x. Parity operator operates in these two functions minus h cap x, here also f of x that will be h cap minus x change to h cap plus x, since Vx is same as that of v of minus x. Hamiltonian means h is equal to p square divided by 2m plus Vx. F of minus x is written as the parity operator of f of x minus h cap x, that is the parity operator of f of x. Look these two, the result will be 0, since f of x is an arbitrary function. F of x is arbitrarily chosen, then the commutation relation between that of parity operator and Hamiltonian will be 0. Okay. So, with this visual lecture we understand what is the basics towards parity operator, definition of parity operator, its representation and mathematical formula, Hermiticity of parity operator. Since the parity operator is Hermitian, we say that eigenvalues are real, then the eigenvalues and eigenfunctions of that of parity operator. This is the eigenvalue equations of that of parity operator, and with that help we use the even function and odd function, the help of eigenvalues and eigenfunctions of parity operator, and then orthogonality of that of psi plus and psi minus, and a question related to that parity operator, the commutation relation between parity operator and Hermitian operator, that means these two are commute with each other, since the result will be 0. So, with this useful and informative notes, let me wind up this session. Thank you.